All right, let's jump right in. Today we're going to crack the code of organic chemistry. Think of it as learning the secret language of the very molecules that make up, well, everything.
These aren't some far-off abstract things. We're talking about the molecules in you. They're in your DNA, the food you just ate, even the medicine you might take. They are literally the building blocks of life.
So, take a guess. How many of these compounds do you think there are? Thousands? Hundreds of thousands? Nope, we're talking millions. And that number just keeps climbing. It's this huge, sprawling universe of molecules. So how on earth do you make sense of it all? You need a system, a code. And that's exactly what we're going to do today. We're going to crack that code.
Okay, so here's our game plan. First, we'll get a handle on just how massive this world of compounds really is. Then, we're going to meet the superstar of the show, carbon. After that, we'll figure out how chemists draw these things, learn the grammar for naming them, and finally, see how they're all sorted into different families. Ready?
So, to really get this, we've got to rewind a bit. See, for a long time, chemists thought the world was divided into two camps, and one single discovery was about to blow that whole idea wide open, changing everything we thought we knew about where these molecules of life actually came from.
Back in the day, everyone believed in this idea of a vital force. They thought organic compounds had this special magic, something that could only come from living things. But then, in 1828, this guy, Friedrich Weyler, comes along and completely flips the script. In his lab, he makes urea, which is totally organic, from something totally inorganic. That one experiment, it just shattered that old vital force theory. It proved that chemistry is chemistry, whether it's happening in a plant or in a test tube.
Okay, so if there's no magic life force, then what's the deal with carbon? I mean, what gives this one element the power to form millions and millions of different compounds? There has to be a secret, right? Well, there is, and it all comes down to a couple of really unique properties.
First up, superpower number 1, catenation. It's a fancy word, but it just means carbon is amazing at linking up with itself. It can form these super long, super stable chains and rings. Seriously, it's like the ultimate molecular Lego. It can just keep clicking together.
And its second superpower? Tetravalence. Every single carbon atom has 4, count them, 4 spots to form bonds. This is huge. It means it doesn't just build in a straight line, it can branch out in 3D, creating all these complex, beautiful shapes that are absolutely essential for life. It's like a tiny little hub with 4 connection points ready to go.
So that's great and all, but how do you draw a 3D molecule on a flat piece of paper or a screen? Well, chemists came up with a clever little code for that, the wedge and dash formula. Take a look. That solid black wedge, that bond is popping out of the screen, coming right at you. The dashed line, that one's going into the screen, away from you. And the normal lines are just flat, in the plane of the screen. It's a super simple, but really powerful way to see in 3D.
Okay, imagine having to write out every single letter of every word all the time. It would take forever, right? That's why we have shorthand. Well, chemists felt the same way. With millions of compounds, drawing out every single atom and bond would be a nightmare, so they came up with their own versions of shorthand.
Let's start with the long-form version. This is the complete structural formula. As you can see, it shows everything. Every atom, every bond, it's all there. It leaves no room for doubt, but man, it takes a long time to draw.
Now to speed things up, we've got the condensed formula. See what's happening here? We're just grouping the hydrogens with the carbon they're attached to. It cleans things up a lot, gets rid of most of those lines, and it's way faster to jot down while still showing you how everything's connected.
And that brings us to the grand finale, the real pro-level shorthand, the bond line formula. This is what you'll see most of the time. It's so elegant. Every point and every end of a line is a carbon atom. The lines themselves are the bonds between them. And the hydrogens, you don't even draw them. They're just implied. It's fast, it's clean, and it's the go-to language for organic chemists.
Okay, so we can draw them, but what do we call them? You can't just have nicknames for millions of different molecules. It would be total chaos. You need a set of rules, a universal grammar, so that a chemist in Tokyo and a chemist in Toronto are talking about the exact same thing. And that's where the system called IUPAC nomenclature comes into play.
The absolute foundation of this whole naming system is the number of carbons in the main chain. It's like the root of a word. You just have to learn a few prefixes. As you can see here, 1 carbon is meth, 2 is F, 3 is prop, 4 is buts, and it goes on from there. That prefix is the starting point for the molecule's official name.
Once you have that root, it's really just a 4-step process.
It's like a little puzzle every time. First, you find the longest possible chain of carbons. That's the parent. Step 2, you number that chain, but you have to do it in a way that gives any little branches the lowest possible number. Third, you give a name to those branches. And finally, you put it all together. List the branches alphabetically with their numbers out front, followed by the parent name. Simple as that.
All right, time for a quick challenge to see if you're following along. Let's talk bonds. Every single bond is what we call a sigma bond. That's the strong core. But when you have double or triple bonds, you get extra bonds called pi bonds. So with that little refresher, take a look at this molecule on the screen. Go ahead and pause and try to count up how many sigma bonds and how many pi bonds are in there. Okay, you ready for the answer? The molecule has 10 sigma bonds and 3 pi bonds. How'd you do? Here's the breakdown. Remember, every bond, single, double, or triple, has 1 sigma bond, so you count all of those up. Then, the double bond adds 1 pi bond, and the triple bond adds 2 pi bonds. Add them all together, and there you have it, 10 sigma and 3 pi. Nice job.
So we can draw them, we can name them. What's next? Well, the last piece of the code is figuring out how chemists organize this massive library of molecules. They group them into families, kind of like in biology, based on what they look like and how they act.
The first big dividing line is pretty simple. Is it a chain or a ring? If it's an open chain, doesn't matter if it's straight or branched, we call it acyclic. But if those carbons loop around and connect back on themselves to form a ring, we call it cyclic. Chain or ring, that's the first cut.
But what really gives a molecule its unique personality, its character, is something called a functional group. Think of the carbon skeleton as just the boring frame of a house. The functional group is like the kitchen or the workshop. It's where all the interesting stuff happens. It's a specific little cluster of atoms that basically tells the whole molecule how to behave.
And there are tons of them. For instance, if you spot an OH group tacked onto a carbon chain, boom, you've got an alcohol. See a COOH group? That's a carboxylic acid. Even a double bond between 2 carbons is a functional group. That makes it an alkene. A triple bond makes it an alkyne. These little groups are like name tags that tell you exactly what family the molecule belongs to.
And this is maybe the most important takeaway. The functional group isn't just a label. It is, as our source material puts it, usually the site of chemical reactivity. In other words, it's the hot spot on the molecule. It's the part that does stuff, the part that reacts. It's where the action is.
So there you have it. We've learned the alphabet, carbon. We've learned the shorthand for drawing it, and the grammar for naming it. You basically have the keys to decode the language of molecules. You can now start to read these chemical conversations happening all around us and inside us. The only question is, what will you choose to read next?